Well, hey, with that said, what I'd like to do is I'm going to go ahead and get our next speaker lined up. It is someone who, it's funny, Phil, you gave us a good introduction talking about regexes and how your regexes usually lead to kicking, screaming, and crying, which is a very similar situation for me. And to be completely frank with you, one of the things that I find myself constantly stumbling and over and trembling about is PowerShell and PowerShell obfuscation. And our next speaker, Joe Petroske, has actually decided, you know what, Matt, why are you going the long and hard way about this? Why don't you take the smart way by just applying linear regression towards it? And as soon as I read this topic, I was like, oh my gosh, we have to have this because this is a common problem that I think incident responders and threat hunters everywhere face, number one. And number two, what a novel way to approach this. So without any further delay, Joe Petroske, he is here to talk to us about hunting PowerShell obfuscation with linear regression. And just a reminder, everyone, hop into the Slack and keep your comments and questions flowing so that way we can get some stuff out of Joe. But Joe, on to you. Take it away. We're looking forward to it.
All right. Thanks so much, Matt. So thanks everyone for attending today. Thanks so much to Sands for having me. In particular to Jen for kind of being my handler and walking me through this whole thing. So thank you for your help. And we're gonna talk about some cool stuff today. So I'm really enjoying the Threat Hunting Summit 2020 so far. And let's just keep this rolling. So let's see here, go to the next slide. There we go. So here's what we'll be talking about a little bit today. So I'll quickly introduce myself and then I'll kind of get into like what it is specifically that we're trying to look for here. And we're going to find some patterns that show up and in relationships that you can find in the kinds of PowerShell evil commands that we're going to be looking for here. And then we're going to do some applied statistics stuff to go try to find that evil stuff. So that's what we'll be doing here for the next little bit. So here's me. Been doing blue team stuff for about 16 or so years, the past like 10 or 11 in incident response and threat hunting. I work for Target with, you've seen already a bunch of my amazing colleagues already. So I get to do really cool stuff with David and Fred and Kat all the time. And so my job is pretty awesome. Next year will be my 6-year service anniversary with the company already. So I don't know quite where that went, but yeah, that's me. So enough of that. Let's get into what we're talking about. So if you're wondering whether this is applicable or not, like really don't take my word for it. If you just literally Google obfuscated PowerShell, you'll get like pages and pages of stuff. So tooling, articles about it, things you can do with it, whatever like that. There's really not much of a barrier to entry here if you want to use these things for malicious purposes. So this is something like we as threat hunters should kind of have in the back of our minds and kind of be thinking about, right? We should be looking for this kind of stuff. This is applicable to us. So then what specifically are we going to be looking for? Well, let's think about this a little bit. We're looking for PowerShell commands that have been doctored up in such a way that you can't tell what they do, right? So, and why would you do that? It's to defer people that do stuff like reverse engineering, incident response, threat hunting, or whatever. And why would you try to throw them off your trail? Well, it's because you're probably trying to do something evil with it. So what is our goal in looking for this? It's going to be, so I'm going to say that we're not really necessarily at least trying to build static detection for obfuscation. Reason being is because there's pretty much as many ways as you can obfuscate something in PowerShell. Like you're really only limited to your imagination and the depths of your depravity, really. So there's not really going to be a way to really detect all that or really get detection for the results of these commands. Instead, what we really want to do is just figure out all the PowerShell that's being run at scale across wherever your enterprise is, and then boil that down into something that you can say like, okay, if there's obfuscated evil things, it's most likely to be in this manageable subset. So that's what we're trying to look for. This is a big data set reduction exercise. Okay, let's look at some examples. So here is a PowerShell command. So in the absence of any other kind of context or knowledge, you can read this and go, okay, well, there's some plain text variable definitions here. There's like a plain text verb. There's some concatenating. Okay, it looks like they're building a user prompt, right? So this is a PowerShell command that you can kind of tell it's fairly self-explanatory what this is doing. I would consider this to be something normal, benign, and non-obfuscated. On the other hand, so here's something else. So here's another PowerShell command. And I have no idea what this is. And that's really the whole point. There's like some sort of encoded mess at the bottom of this here. There's like a mixed case command up at the top here. I have no idea what this is, and I know all I really know is that if I saw this in my real world environment, it's time to roll heavy on this, and the blue team is going to burn this with the sacred cleansing fire, right? So this is obfuscated. The intent of doing this is to make it sure that someone who's looking at this doesn't know what it is. So let's figure out what specifically we want to look for. So I also get to work with Paul Melson, who really kind of gave me this like cool piece of advice that really stands the test of time. Don't try to identify what that obfuscated command does. Don't try to detect what it does. Instead, just identify that it's obfuscated in the first place. Just go find the obfuscation. And that in and of itself is enough to make us go, okay, now my suspicion is raised. I probably need to go look at this much more closely, and we might have a problem going on here. So let's talk about how we're going to start actually hunting this. So there's going to be some prerequisites before we can get this off the ground. So job one is we've got to make sure that we've got some sort of endpoint logging going on. And like I realize that budgeting and bandwidth and that kind of stuff is a real thing. It's a real concern. I will submit to everybody that if you're really serious about doing hunting on your endpoints, you got to get logs off your endpoints. In this particular case, there's a few different options, excuse me, for logging PowerShell. Sysmon event ID 1 is pretty good. In this case, I actually used event ID 800, which captures a bunch of good stuff like the full PowerShell command plus any switches run in it. So that pretty much is really what I wanted here. So if you are logging these things off your endpoints, then you need a place to collect them all into a central logging repository thing and a place to search that. So I'm not going to sell or recommend any tools here. If you've rolled your own, if you're using something like Elk, if you're paying for a tool like Splunk, whatever, use something that works and whatever's in your budget. That's my favorite kind of tool, right? So do what works for you. Once you've got this stuff in your central searchable collection point, then we're going to need some sort of analysis package for this thing, a data analysis package, and a plotting, graphing, visualization mechanism. So again, here, you use what tools you like, use what tools you work. In this case, I use the Jupyter Notebook as my analysis engine. So if you're not familiar with that, it's a wonderful, beautiful thing. You can think of it as kind of like a live GUI kernel for Python that lets you kind of do stuff on the fly and change things on the fly. And when you're good at trial and error like me, it's super useful. You'll need a data analysis package. I use Pandas. In fact, specifically, I was using the Windows Anaconda distribution, which has a lot of different ones. So I use Pandas in this case. But if you're more familiar with R or something like that, go nuts. And then you'll need a way of visualizing all this stuff. So there's different visualization packages. I use Plotly Express, again, due to simplicity. Total cost of that whole analysis package is $0. So that's another reason why I picked what I did. So let's talk about what we're going to be assuming here. If we're going to be looking for evil PowerShell, there's probably going to be some similar consistent themes that are going to come up here. So if it's evil and obfuscated, it's probably going to run fairly early in the kill chain. So like, for instance, if you saw Chris and John's talk yesterday, where they went from initial fish all the way to domain admin, all the way to Sodinokibi tragedy, right? So there was a lot of PowerShell in there. Where's the obfuscated stuff though? It was fairly early in the kill chain. So it was like within the first couple phases of the attack. That's where you saw that. It's probably gonna be run directly from a shell, right? So we're talking about an adversary who's gotten probably initial foothold someplace, probably on a popped endpoint or something to that effect. They're operating only in memory. And the real pros will continue to probably operate only in memory, so they don't want to drop anything to disk. So we're not going to be looking for a dropped PS1 script file on disk someplace. So this is run really only from the shell. And that fell off the bottom of the screen. Probably under a user context, right? So early in the attack lifecycle here, we're talking about adversaries who probably haven't been able to elevate privileges yet. So maybe they popped a user who does have some elevated privileges, but they're not domain admin yet. So in other words, when we're finding this stuff, all is not yet lost, right? They haven't completed mission yet. However, time is of the essence. So we got to move on this. Okay, how are we going to collect this data? So what I did in order to collect a corpus of data to begin hunting on. So look for something like this. Here's sort of like a pseudo search, but collect this over some period of time from across your enterprise from as much as you can get and then deduplicate it. So in other words, get event ID 800, and come up with a regex for whatever users look like in your environment, and then exclude anything that runs off a PS1 or a script file, right? So in other words, these are PowerShell native commands run from the shell, logged into event ID 800, and run by something under a user context. So when I did this, the total cardinality of stuff, I ran this for about 3 weeks across my entire enterprise and like just got as much PowerShell as I could possibly get my hands on. Total cardinality, that was pretty big, right? So it's about 30 million things. But we're going to actually visualize this in a scatter plot, which means that we're going to want to deduplicate it. The reason being is because when you scatter plot non-deduplicated stuff, the data points just kind of stack on top of one another, and it doesn't give you any additional information. So you might as well just operate on unique data. So that's what we want here. And when I boiled that down to deduplicated, I dropped about 3 orders of magnitude. I was down to about 7,000 things. So that was kind of cool, which kind of makes sense, right? So most of the stuff you're going to find is automated script things that run across your environment maybe multiple times per day by admin type things, right? So your mileage is obviously going to vary depending on the size of your enterprise, but that's a fairly big data reduction just like that. And then what I did is I took that corpus of data and intentionally stuck some things in there. So Fred and I were playing with a bunch of different obfuscation tools. He was messing around with Daniel Bohannon's invoke obfuscation stuff, which is super cool. Like if you've never messed around with that, go check it out. But Fred had this like giant body of things that he obfuscated with this tool, and he just gave me a bunch of them. So I picked 6 of those at random and just appended them to the end of my data set, just so that I knew that I had some needles to find in a haystack, right? So here's the patterns that we're going to be looking for here if we're going to try to find obfuscated stuff in that mess. If you think about what obfuscated commands have in common, they've got a couple things going on here. So there's going to be some sort of encoding mechanism in there that turns whatever the plain text that would have been in that PowerShell command into illegible stuff. And then, of course, the way to turn that illegible stuff back into something that'll actually run, right? So both of those things are going to be present in that command, which means that the length of that command is probably going to be getting longer and longer because it has to include both of those things. So let's sort of use this to our advantage here. If you think about it, the longer the command you're looking at is, the more things that you're going to find as far as character types, those numbers are also going to increase as the size of the command increases as well. And we'd probably roughly intuitively expect this relationship to be linear. So in other words, the longer a command is, the more letters you're going to have in it, the more digits you're going to have in it, the more special characters you're going to have in it, etc. So that should make intuitive sense. So then the question becomes like, okay, well, if we're going to use that relationship to go find obfuscation, which one should we go after? Well, there's a bunch of options that we've got here. So we can look for things like, I don't know, dollar signs, right, which denote PowerShell variables. We can look for string literals, quote marks, double quote marks, grouping characters, switches between uppercase and lowercase. And then actually, like Fred gave me a good idea. It's like, why not just look for letters and digits? Okay, cool. So let's check that out. And we'll have kind of like a bake-off here and see like which one of these best explains our data. So we need to figure out actually a quantitative way to figure out, well, which of those is best, right? So we can eyeball it, but we can actually get this quantified and get some numbers on it. So you can measure the strength of the relationship between your observed data and what you'd expect it to be. So in other words, if we expect this data to be linear, then there is a line that most closely fits the observed data. And the process of finding that line is what we call linear regression, right? So it's the technique for taking your observed data, graphing it, and then finding the line that most explains or best fits that data. A linear regression has a property, without getting into too much stats here, called the R-squared statistic, which is basically the amount of variation that you found in your data that can be explained by the regression line that you just drew. In other words, it's a measure of how closely that line fits the observed data on a scale of 0 to 1. 0 meaning it's basically not a fit at all, and 1 meaning it very closely and tightly explains the data that you're actually looking at here. So what we're trying to do is find the R-squared statistic, a measure of how much your observed data differs from what you'd expect, and the expected stuff is what you'd find along that line. Okay, so back to my initial question here. We've got some options here on which character we want to do a regression on. Well, let's just do a linear regression on each of those options here and see which one has the highest R-squared value. So that's really going to be our best fit to the data and most closely explains it. So, okay, let's do basically a scatter plot between the length of the command and the count of things like dollar signs and grouping characters and letters and numbers, et cetera, and which one works best. Well, it's actually this one right over here. So what it wound up being is the just alpha characters, counts of letters, are most closely related to the length of the command. So I tried a whole bunch of them here. There's a couple other decent options here. You have an option for something called a multiple regression. So in other words, using multiple independent variables to explain the dependent variable. In this case, it just wasn't needed. The R-squared value for just count of alpha was so high that it was like, well, that's really all I'm going to need right here. So that's what we can go forward with. And if you think about this a little bit, like if you kind of step back, and you can probably say like, actually, yeah, that makes sense. If you're looking at a big corpus of PowerShell commands run across your environment, it's probably mostly non-obfuscated, right? And in best case, it's completely non-obfuscated. You didn't find anything evil in there. So you would expect that to be mostly things that are human readable, were written in such a way that they could be understood. And it's going to be, in this case, mostly letters. And that kind of makes sense. So if you define very normal PowerShell commands as they're non-obfuscated and are mostly letters and you can human read it, then what that means is we can find the opposite of that. And that's what we're looking for as an anomaly. We're trying to find things that aren't mostly letters and therefore are mostly likely to be obfuscated. So that's what we're going after right now. So when you do linear regression on really any analysis package, you'll get a bunch of information about that regression. It's called, you might have heard of it as like ANOVA, or analysis of variance, or regression statistics or something like that. This is what you get out of pandas. So a couple things jump out here. So the first thing in the top right is the actual R-squared value for that linear regression. And on a scale of 0 to 1, this is like 965. That's about as high as you can really get in the real world. And then if you remember like what the graph of a line looks like, so if you go back to like 8th grade algebra, it's like y equals the slope of the line times x plus the y-intercept, like y equals mx plus b. That's really what we're finding right here. And you said like, yeah, when am I ever going to use that? Well, today's the day, right? So here are those things down here where the arrows are pointing to. So there's actually the y-intercept and slope of the regression. So we're pretty confident that the regression line that explains this data is going to be about y equals 0.855x minus 10. There's some additional cool regression data or metadata. The P of T values is basically an explanation of like, what is the chance that this data was just really by chance and that there isn't actually a relationship between these two variables? And it's 0, right? So there's actually really no chance that there is no relationship between these two variables. So this is a really good linear regression, and this is going to be useful for us. So let's scatter plot it finally. So here is the initial scatter plot of the length of all the commands I found and the count of the letters in all of those commands. And of course, what jumps out at you right away is two things. So one, there's a couple things way off the end of the chart here, and the rest is way over there, clustered around the origin. So maybe let's zoom in on that a little bit. So this is actually really what most of the data looks like. It's fairly clustered really tightly around that regression line, which is what we expect. And it looks like we can really start using this now to find anomalies. Okay, so if we now know what our graph looks like, we can now use that to find outliers. So we got to define like, okay, if we think this is what our data looks like when visualized, what are things that would look abnormal based on that visualization? So if we say that things that are really close to that regression line are what we would expect, right? That means that the farther you get from that regression line, that's the most likely to be things that we wouldn't expect. In other words, that's probably where obfuscation is going to live if it exists. And I also threw kind of just a hard length cap on this thing. When I was looking at all my data, I really didn't find any more than a couple of instances of a command that were longer than 250 characters. So I just set a hard threshold here and I said anything longer than that I want to know about. So then what I did was I tried to define a range around that regression line to say, okay, outside of this range, this is what I'm going to define as an outlier, and this is what I want to know about. And in my code, I did that with a variable so I could control the width of that band. So you can kind of doctor this up to as you need it. So if you make this range wider, this will reduce your false positive rate, but it might result in you missing things that you would have wanted to find. If you make it narrower, you're probably going to be more likely to find anything that there is to find at a trade-off of having more false positives. So kind of set this where it works for you, and you can kind of play around with it a little bit. So when you graph it with a band defined, it looks a little something like this. So I set this to, I believe, like 23 times the 95% confidence interval for what the slope of that line was. And you can pretty cleanly see like, okay, most of the stuff is inside those two red lines, and there's some stuff outside it. Those look like they probably should be something I want to know about. Doing it this way, return about 8.5% of the initial data set as things that were defined as outliers. So cool, that's a much more manageable number. Like I wouldn't want to look at 7,000 things with my eyes because my attention span isn't that long, but like 600 things, I can probably do that, right? So what I did is I simply spit all that stuff out to CSV and started looking through it. And sure enough, I had originally seeded 6 intentionally obfuscated commands in this data set, and I got all 6 of them. So really, I got a 0% false negative rate. I did find everything that I needed to find. There were quite a few things that wound up looking, fairly weird, right? But they wound up being benign, human readable things that I could explain away. So that resultant set of stuff is enough for a human to go process. So again, I couldn't really automate this away. This was really not high fidelity enough for static detection, but it wound up being a really great hunting exercise and super useful. So I think I got a good win out of this one. So one of the reasons I really like this kind of investigation here is because it wound up being the simplest and most elegant solution was the most effective thing. Right? I didn't need to train some sort of complex algorithm here. Like I didn't need to do anything really ridiculous. It's really sort of like fairly basic statistics stuff gave me the best results. And not only that, but it was really the simplest regression I could do on the simplest use case that I could come up with was the most effective thing. So this is, I think, a really effective way of finding things that are PowerShell commands running in your environment that are the most likely to be obfuscated and the most likely to be suspicious. And this is a repeatable analysis. So this can be iterated. We can do this again and again, and this can be shared with people. And that's what I really want to do today. So really, this is where I say, like, okay, everybody else, please take it from here. This will eventually be on github.com/target. Unfortunately, the approval process for doing that took longer than the time delta between when I wrote this talk and today. So it'll eventually be there. However, what I will do is I will post my analysis notebook in my hallway chat after when I'm done here. So whoever wants it, please grab it and go try this. All right. So I would love to hear back from everyone next week, next month, next year, and tell me like, yeah, Joe, like I tried this in my environment and it worked. I found some stuff and I investigated and this is real world and it works. So I would love to hear back from this. Please go check my code, try it. When I get it up on GitHub, send me PRs, like let's talk about this and make this a cool thing that we can share. So I would love to hear that. And that's really all I got. That's my time. Thank you all for your attendance today. Thank you so much to Sands. And on a personal note, please be safe and healthy out there. Things get scary. Take care of yourselves. Take care of your families, however you define family. And thank you very much.